we look at this, we can see we have our likelihood over here, and then our consequence at the bottom, and you can see where we are. Now what we need to do, of course, is we need to move that from where it is at the moment. We got to move it to the left, as it were, and then down to get it down into, and what we want to do is get it down into our tolerable region in here, which is our ALARP. So how can we do that? Well, the first thing we can do is we can look at our inventories. So again, if we don't need to store a large amount of the material on site because we're doing batches, or we don't need necessarily a lot of the material, then we can manage it by keeping smaller inventories. But of course, as it says there, good process engineering support is vital, so that you have sufficient quantities of material to be able to keep your manufacturing process going. But how we store the material is very important. Some of you may remember the West Texas fertilizer plant that caught fire and eventually blew up. They apparently had 50 times the material that they were certified, or rather they were approved to store on site, which didn't help. So they had far more material than they should have had there. And ultimately what they discovered was, sadly, that the fire was the result of arson. Somebody deliberately set the fire. So storage, very important. Again, geographic layout. As I said, if it's a greenfield site, you've got the opportunity to do this right from the beginning. If it's a brownfield site, you're limited in what you can do. But you can see there we've mapped in the ALARP. Where's the 10 to the minus 3 to the 10 to the minus 6. And it's important to remember that the human body, any more than 4 pounds per square inch, will start to cause severe internal organ damage. And so a blast wave, and again, a lot of companies do use QRA, this is another acronym, quantitative risk assessment. This is where they will employ somebody to come in and do some modeling. They might do some blast wave modeling, they might do some cloud dispersion modeling. They'll look at all of this and they can take this into consideration. So they can map out where is the safest place to be able to position, for example, the office block, if that's where you have all your administrative people and your management, versus where is or even where the control room needs to be situated as well. So we can manage it by controlling where the people are relative to where the major hazards are likely to occur. So we can start to move it towards the right direction, lowering the consequence by proper handling of inventory, proper positioning of people, also containment. So if you've got a toxic material or even a corrosive material that could leak, then you want to have maybe some bunds or dikes on site that can contain that and keep it away from either getting into the water system or getting into the local area. And then we can use non-SIS forms of risk reduction, for example, pressure, mechanical relief. So we can move ourselves down into ALARP. Now what's wrong with this slide? So we've moved ourselves and we're looking at SIL 3. Well, the obvious answer is, why SIL 3? Why SIL 2? Surely if we've met our ALARP target, which is, of course, if we look at our ALARP target, whoops, I'll get my finger in the right spot, we're there. So we may say, all right, let's look at the cost of putting in a SIL 1 SIF, which will get us into the broadly acceptable range, and being safety engineers, we like to err on the side of caution. We could look at the cost of doing that versus just leaving where we are. because not every single application will necessarily need a safety instrumented function or a safety instrumented system. If we have the relevant layers of protection in place, we've done our analysis properly, then we might not need it.